Alright, the final area of study that we're looking at in Unit 3, this is our study of 2, so we went 3, then 1, and now 2. So this kind of puts together a bit of, the movement and field stuff, particularly the electric and magnetic field, to how we can move electrical energy. So one of the things we talk about here with this is magnetic flux. So magnetic flux, a couple of videos there about magnetic flux. So magnetic flux, basically it's about the concentration of the magnetic field. Alright, so it's given a symbol, this one here, one of the Greek letters, a capital one. So if it's about to do with concentration of magnetic field, it has the field strength itself involved, of course, and the area that field is going through. Alright, now also with the area and that, like we could have a field that's going down like this, but if we've got an area that it's going through, and that might be area A, but if we rotate that a bit, I haven't quite got that right there, but if we rotated that a bit, the area of the that rectangular, green rectangular wire, in both cases is supposed to be the same, but it's the field itself is not exposed to that whole area because there's an angle. So the angle needs to the area and the field are to each other. They that needs to be taken into account, and that's cos of phi. And now that angle that we are talking about, we've got a bit of a diagram here. I'll show you. Alright, so here it is. You'll see this again later. But if we've got, shows a coil, but if we've got that is the one edge of a coil, and so the area we're looking down on top of it, the area is hidden from sight, and so what we do is we put a line that's this one here that makes 90 degrees to the front of the coil, which that would be called the normal to the coil, and the angle that we're interested in is this one here, that angle in there. Alright, so the unit of flux is the Weber, WB. Alright, and 1 Tesla is 1 Weber per metre squared. Alright, so 1 Tesla is 1 Weber per metre squared, if we need to go between. Alright, so it's all very well. If we can get a flux, that's nice. The question is, how do we change the flux? As we can. Alright, we can get a light to turn on here, right? So we've got a magnet and a wire coil, and you move that, and the light goes on. And as we'll see, light will only go on when it moves. So what we're interested in is the changing flux and how we might be able to change the flux. So here's 3 ways that we can change the flux. We can have a constant field and move a wire through it. We can have a constant field and rotate the wire, or we can change the strength of the magnetic field. Alright, so there's a little bit more information in your notes about that, right with that diagram. But there's a physicist named Michael Faraday, and he was the one that came up with the equations and the idea about how the electric and the magnetic fields all came together. Alright, the next bit is the next thing we can do is if we can get a flux and we can change a flux, and I've already touched on that we can get, when we change the flux, we can get some electron flow, so we can get some current that's formed, and so that leads us to what's called electromagnetic induction. Electro from electric, magnetic from magnet. So, alright, so we've got that interaction between the electric and the magnetic. And so we induce, by doing that, we induce something. Alright, so we already know from area study 1 that if we move a charge moving in a magnetic field, experiences a force. Alright, so it experiences a force, and so that force depends on how fast that charge is moving, the strength of the magnetic field, the size of that charge, and the angle to the field that it's going. Alright, so we know that. Now, if theta is equal to 90 degrees, then that simplifies down to that the force depends on the speed that it's going, the field, and the charge. So, if we do that like this diagram, rather than just with a single charge with a wire, and as we know, wires have got charges in them, you know, protons and electrons are in wires. So if we take this wire here and we shove this wire to the right, and we've got a field going in, and if we use the right hand push rule, thumb in the direction of V, fingers in the direction of with the field, which is into the page, and then when we do that, our palm pushes the positives. So as we can see from this diagram, the positives would get pushed up that way, and of course the negatives would then get pushed in the opposite direction. So because there's now become this separation of charge, we've done what is known as inducing a current. So we have induced current. Alright, and so that's from the force on the charges moving at a certain velocity in a magnetic field, and those forces, those charges, happen to be in a wire. So the electric current that is produced will be proportional to the change in flux with time. So you stick it in more quickly, and as it shows, if you stick something in more quickly, then the force is stronger. If the force is stronger, it's going to shove these down here more quickly because of the stronger force. Alright, so there's just a reminder about the right hand push rule. And just in bold there, no current is produced when the wire moves parallel to the field. Okay, so what we're talking about is if the field direction and the velocity were the same, then there'd be no current produced. So and that's to do with that sine phi bit that we ignored when it was at 90 degrees. Okay, so if it's at 90 degrees, we get our maximum current. If it's at 0 degrees, we get no current. And if it's at any other angle, it's something in between. But in this course, we're only interested in 0 and 90. Alright, so let's have a look at example. The student places a horizontal 5 centimetre square coil of wire into a uniform vertical magnetic field of 0.1 Tesla. How much flux cuts through the coil? She then pulls the coil out at a rate takes 1 second for to lose the flux. She finds she gets a current of 2 milliamps. Puts the back in at the same rate. What will she observe? Pulls it out again twice as fast. What current will be induced? Now steadily rotates. 2 seconds through 180. Describe that will be induced. Right, let's have a look at all of this sort of stuff. So first of all, there's a fair bit in this. So let's just look at each bit carefully. So the first one, how much flux cuts through the coil? Alright, so it's a 5 centimetre square. So the area, 5 centimetres square. Now remember, we need it in metres squared. So 5 centimetres is 0.05 of a metre, and length by width, because it's a squared, it's that squared. Magnetic field is 0.1 Tesla. And let's read the question again. Horizontal into a uniform vertical. Alright, so horizontal and vertical at 90 degrees to each other. So we don't, when they're at 90 degrees, it's just BA. And so that's 0.1 times 0.05 squared, which we then get to be 2.5 by 10 to the minus 4 Weber. Alright, so that's how much flux. So she pulls the coil out at the rate that it takes 1 second for the coil to lose all the flux. While the coil is coming out, she gets 2 milliamps. Alright, so coming out of the field, 2 milliamps. It's registered on the ammeter connected to it. If she puts it back into the coil at the same rate, what current will she observe? Alright, so it says the same rate. So the same rate, that is key. So B into at same rate. Alright, and remember the induced current was proportional to the rate of change of flux. And so we've got the same rate but opposite direction. So same rate, opposite direction, same current, opposite direction. So it would be a 2 milliamp current. And to indicate the opposite direction, because it says in the question there plus 2, so therefore it's minus 2 milliamps. Alright, so that's that. Part C, if she pulls it out again twice as fast. So this time we're going twice as fast out. So twice as fast would be twice the rate. Alright, so again, current is proportional to the change in flux with time, so it's half the amount of time. So twice the rate, twice the current. Alright, so the current would be plus 4 milliamps. Alright. D. She now rotates the loop while it is fully in the field in such a way it takes 2 seconds to rotate through 180 degrees. What? Describe the current that will be induced. Alright, so say we've got a field going down here, like so, and we've got this coil, got it there, and we rotate it, whoops, we rotate it until it gets to there. So this end ends up over there. So what is happening? So we've got a change in flux. So let's think about what happened before when we just moved it out. So we've got a change of flux. So before, when it took the first 1 second to move it out, so out in 1 second before, so we went from a flux of so 2.5 by 10 to the -4 Weber down to 0 in 1 second, and that gave us plus 2 milliamps. So effectively, when we rotate, when we get it in this vertical position that I've just gone here, we've got flux coming through there of 2.5 by 10 to the 4, and in this case, when it's vertical, we have no flux. So it's the same thing. It's from 2.5 by 10 to the -4, the little negative's not very big there, to 0 in 1 second, because it's taking 2 seconds. So here it's 0 seconds, 1 second, and it's 2 seconds till it's rotated 180. So it looks like we're getting 2 milliamps. And then when we go the other bit, we get another. So then it's going from 0 back to the 2.5 by 10 to the -4. Alright, and so that would then mean we might get -2 milliamps, which is what we did in the previous question when it was put back in. Alright, but opposite direction. Alright, so that's essentially what we get in that particular question, and we'll talk a bit more about that when we get to induced EMF a little bit later. Alright, so we talked about that. We can get some current, and so that now needs us to a thing called induced EMF. Alright, so induced EMF. EMF is an interesting term. So EMF is electromotive force, it's called. Electromotive force. Alright, so it's an old term that's used, but remember back here, a few pages back, and I won't flick back to it, but when I put that wire in move a wire in the field at a certain speed, you get a force on the charges, and it separates those charges. So there's some motion involved, there's a force involved, and it's electricity. Alright, so it says here, when a current is induced, an EMF is also induced, right? Because you've got that separation of charges. So you get a voltage. Alright, so one of the scientists who work in this area is Michael Faraday. Mentioned him before. He concluded the strength of the EMF depends on 3 things: the speed of the coil or the magnet, the strength of the magnetic field, and the number of turns in the coil. So we just talked about one wire there, but we could have a whole coil of wires. So it led to what's called Faraday's law of induction, where the EMF, the voltage produced, depends on the number of turns, the rate of change in flux, and also negative. So it's opposite. There's an opposite direction thing. So number of turns in the wire is N. Up the top there identifies the change in the flux and the time taken. Alright, so if we have a conductor moving in a magnetic field with constant velocity, alright, then we have to apply force. Alright, we apply force, and there's a magnetic force. Now, remember when we earlier in the previous area of study, that magnetic force was opposite direction. So that's opposite direction because the currents that's produced, the electrons that produces its own magnetic field and tries to oppose what's happening. So we're applying a force and we're trying to oppose that force by this magnetic field. All right. So, and also remember, that will depend on the current, the length of the wire in the field, and the field as well. So if we assume then there's no energy loss, then what we've got is some mechanical energy here, and we've got some electrical electrical energy over here, and so that mechanical energy, which would be work done, is change in energy, F times D, the force that we apply times the distance, will be EQ, and the E, of course, is the EMF that's produced, times Q, the charge. All right, so a couple other bits and pieces. So if the force applied is equal to negative magnetic force, and so that's negative ILB, and the distance, if we use V equals the D over the T, then the distance is V times T, so times VT, and the EMF, and of course the current is charge over time. So the charge then would be IT equals the charge, so times IT. Alright, so we've got some cancelling outs that can happen here. There's the current on both sides, there's the time on both sides, so we don't actually need them. So the EMF, I forgot the MF here, is equal to negative VLV. Alright, so it depends on, as Faraday suggested, the field, the number of turns in the coil or the length of the coil, and the speed, all into that. Alright, so that thing there is something we're interested in. So let's have a look at an example. Alright, before we start this here, I don't know what's going on there, why it's a little alpha, it should be micro Tesla. Alright, so what is the EMF which could be induced across the wings of a Boeing 747 with a wingspan of 64 metres flying at 990 kilometres per hour through the Earth's magnetic field? Take the maximum magnitude of the Earth's magnetic field as 60 micro Tesla. Alright, so what do we need to know? Well, first of all, our induced EMF is BLV, if it's in its magnitude. Alright, so we're not worried about whether it's positive or negative, so maximum. Alright, so the V is the thing here, because we're given V at 990 kilometres per hour, and so to get to metres per second we need to divide by 3.6, and when we do that we've got 275 metres every second, which is a lot. Alright, so our EMF produced is our magnetic field, 60 by 10 to the minus 6 for micro, times the length, 64 metres, times 275 metres per second. Put all of that in your calculator, and you end up with 1.06 volts. So not much gets produced across the wingtip to wingtip of a Boeing 747. Lucky that, because we don't want to be zapped. Alright, so there's one example, another example. Student winds a coil with an area of 40 centimetres squared. Didn't come out very well, but it's centimetres squared. With 20 turns. So let's put it down. Area equals 40 centimetres squared. We need to change that to metres. Alright. So 0.0040 metres squared. Okay, there's 100 centimetres in a metre. 100 times 100 is 10,000, so that's why its decimal points moved 4 places. What else have we got? N is 20. He places it horizontally in a vertical uniform field, so our field is 0.1. Vertically and horizontally in a vertical, so we know it's 90 degrees towards each other. We don't need to worry about any direction. Connects it to a galvanometer with a resistance of 200 ohms. So part A, how much flux passes through the coil. So the flux, of course, magnetic flux, sometimes you see a little b here, is B times A. We don't need to worry about the area part in this one. So in here, 0.1 Tesla times 0.0040 metres squared, which then is 4 by 10 to the minus 4 Weber. Alright, part B. Part B is, it is then withdrawn from the field in a time of 0.5 seconds. What would be the average current reading on the galvanometer? Alright, so B, EMF. The EMF produced is the change in the flux with time. In fact, it's a bit more than that, because Faraday said negative N change in flux with time. So the EMF produced would be the negative of 20 times the change in flux. Well, we just figured out what the flux was, and that's 4 by 10 to the minus 4, and that's over 0.5 of a second. Alright, so I've done this slightly different in the notes, but you get negative 0.0 0.16 volts. Now the negative just it refers to directions, of course, it's opposing the direction. So if we've got a voltage of 0.016 and that voltage is connected to a circuit, now this is where the resistance comes into it, because what we know from our old friend Ohm is V equals IR, and the question was asked us about what the current reading would be. So the voltage we've got is 0.016 times 200, so we divide both sides by that, and what we then get is a current of 8 by 10 to the minus 5 amps. Alright, so the notes, yeah, there's a little bit of an error there in the notes in terms of what's written there in terms of Ohm's law and getting the current, but the answer is correct. It's just the line above is not coming out all that well. Alright, so what do we got to do? We can get a current, we can get a voltage, and we've got to change the flux. How do we change the flux? Well, there's a number of ways. First way is like this one here. Get a wire, shove it, and then you get a current produced. So we can move the wire. Right? So that's the first one. The second way. Right, so the next way is by rotating a coil and the loop in the field, and one of our earlier examples had this in it. So you got the whole, there's the loop at 90 degrees, you got the whole area exposed that can go through. You then rotate the loop, and so that area that the flux is going through gets smaller, and then you get to 90 degrees, and when you're at 90 degrees the flux going through it's at zero. So maximum flux here at there, zero flux there, and then we keep rotating the coil, and so we then get into a negative flux. Again, that's just direction. It's the field's going through the coil, and I'll talk a lot more about that a little bit later when in the next lesson we talk about generating electricity, and then your EMF is changing flux with time, and so and again I'll talk about that, and so your EMF graph looks like that one there. Alright, so it's pretty easy to induce an EMF. Alright, so under that there's more information about both of those in your notes. But what it is, it's important, and the last bit in your notes there, a little bit of red, notice the instantaneous gradient. So the gradient of our flux here is zero. EMF. The gradient of our flux here is its largest value. Here's our largest value of our EMF there. I shouldn't put it with a. I should put it with a dot, and so on. Okay, back to a zero here. Gradient, back to that. All right. So, and a bit more on that later. So the EMF produced, and that squiggly thing there is used for EMF. So our EMF is negative change in flux with time for one particular loop in a coil. If you do more loops, you multiply it by that. Alright, so that's there in your notes as well. Alright, the last little bit in your notes, and there's a lot more words than I'm going to put here. How we can change the flux is we can change the field strength. Alright, so here's our magnet now. So we've got our magnet, We can shove the magnet, leave the magnet stationary, and then you get no current at all. Shove your magnet in, you'll get a current, and it shows it in that direction. Pull your magnet out, and your current will be induced, and that'll be in the opposite direction. Alright, so there's a bit more words about that, but in your notes, but essentially that's it. So we can change the flux in a number of different ways. Alright, so now you've got some text questions. Don't forget to look at those videos. Don't forget to ask for clarification on anything you're not sure of.